Imagine a weapon so powerful it can wipe out an entire planet in seconds. No invasion, no warning, just gone. That's the Death Star, the most infamous superweapon in sci-fi history. But could the Death Star actually work using real science? What kind of energy would it need? Could a space station survive firing such a weapon? And if someone did try to build it, would it destroy itself before it destroyed a planet? Let's break it down. First, we need to define what destroy actually means. The Death Star doesn't just crack a planet. It doesn't melt the surface. It completely overcomes the planet's gravitational binding energy, the energy holding every atom together. For an Earth-like planet, that number is staggering. To fully disperse the planet Earth into space, you need roughly 2 × 10⁻32 joules of energy. That's equivalent to trillions of nuclear bombs, or the sun's total energy output for several days, or several million times more energy than humanity has produced in its entire existence. And crucially, that energy has to be delivered almost instantly. A slow delivery just heats up the planet. It's a fast energy that unbinds it. So already a real Death Star is in serious trouble. First, let's talk about the power source problem. Where does that energy come from? Star Wars films vaguely suggest hypermatter reactors, exotic matter, or energy harvested from stars. Let's test the most realistic idea, stellar energy extraction. The sun outputs around 3.8 × 10⁻26 watts. If you somehow manage to capture every single joule of energy it emits, you need around 6 days to store enough energy to destroy the planet Earth. And that assumes 100% efficiency, no losses, perfect containment, and no radiation damage. So in reality, you'd need weeks or months of stellar output, stored safely inside a moon-sized battle station. That alone pushes us far beyond known physics. Even if you could generate or capture the required energy, where would you put it? How would you store it? There is no known material that can safely store energy on this scale. Chemical fuel cells would not even come close. Nuclear fuel would still be orders of magnitude too small, and capacitors are laughably inadequate. You need some sort of negative energy density, exotic vacuum energy, or physics we don't yet understand. And here's the real problem. Energy wants to escape. Containment fields would need to withstand extreme radiation, thermal runaway, gravitational stresses, and quantum instability. A single failure point, one fluctuation, and the Death Star would become a self-destructing artificial star. Which, ironically, is exactly what keeps happening in the Star Wars films. Now let's say somehow you solve the energy generation and storage problem. Now you need to fire it. The Death Star weapon appears to be a coherent energy beam, similar to a laser but vastly more powerful. But lasers have a huge problem at scale, and that problem is called beam divergence. Even the best real-world lasers will spread over distance. Over planetary distances, that spread becomes enormous. To keep the beam tight enough to shatter a planet, you'd need a focusing lens hundreds of kilometers wide. You'd need a perfect alignment across a vacuum, no interference from dust, plasma, or magnetic fields. And that's before we even consider the recoil. Firing a beam with that much momentum would exert a force capable of knocking the Death Star out of orbit, tearing its internal structures apart or collapsing the fire chamber itself. Newton's third law does not care about films. Then there's the heat. Energy conversion creates heat. Always. Even with near-perfect efficiency, firing the Death Star would generate insane thermal loads. We're talking trillions of degrees locally, radiation capable of sterilizing the internal compartments of the Death Star, and structural failure from thermal expansion. Space, ironically, makes this worse, not better. In a vacuum, heat can only escape via radiation, which is incredibly slow. So unless the Death Star has city-sized radiators or physics-defying heat sinks, it would literally cook itself from the inside out, which, incidentally, makes that exhaust port suddenly feel a lot more reasonable and necessary. We mustn't forget about size. The Death Star is roughly 160 kilometers in diameter. At that scale, gravity starts to matter. Structural stresses increase massively and materials experience forces they were never designed for. There is no known material strong enough to support a sphere that large under its own gravity, let alone combat damage. Real megastructures like the Death Star would need active structural support, constant force field reinforcement, or continuous self-repair. Without that, the Death Star would slowly collapse, crack, or shear itself apart. Everyone jokes about the exhaust port, but from an engineering perspective, it's kind of inevitable. Any system this powerful would have to vent energy, heat, and pressure. Redundancy creates complexity. Complexity creates failure modes. The more advanced the weapon, the more fragile it becomes, which means the Death Star's real flaw isn't bad design, it's over-engineering. As well as the Death Star, there are other planet killers in sci-fi. The Death Star might be the most famous planet killer in science fiction, but it's far from the only one. In fact, sci-fi is pretty much obsessed with the idea of destroying entire worlds. So let's zoom out for a moment and look at other planet-killing weapons across sci-fi film and television, and ask the same question. Do any of them work any better under real science? First up, let's look at the Doomsday Machine from Star Trek. The Doomsday Machine doesn't fire a giant laser, it doesn't store absurd amounts of energy. Instead, it physically consumes planets, breaking them apart and converting their mass into power. From a physics perspective, this is actually far more plausible. Why? Because mass is energy. If you could efficiently convert planetary matter into usable energy, even a tiny fraction of Einstein's equation, E = mc squared, you'd have more than enough power to keep the weapon running. The real problem isn't energy generation, it's control. A self-repairing, autonomous planet-eating machine would be almost impossible to stop, and almost impossible to keep from eventually turning on its creators. As well as the Death Star, there is also Starkiller Base from Star Wars. Later Star Wars films tried to fix the Death Star problem by scaling it up. Instead of storing energy internally, Starkiller Base drains an entire star and fires that energy through hyperspace to destroy multiple planets at once. This sounds clever until you look at the physics. Removing that much energy from a star would catastrophically destabilize it, potentially triggering stellar collapse, massive flares, or outright supernova. And then there's the beam itself. Energy does not travel cleanly across interstellar distances without spreading, scattering, or interacting with matter. Starkiller Base doesn't solve the Death Star's problems, it actually multiplies them. I can't not look at the Genesis device from Star Trek II: The Wrath of Khan. The Genesis device is one of the most unsettling planet killers ever imagined, largely because it doesn't just destroy. It rearranges matter at the atomic level, converting dead worlds into living ones, or living worlds into something else entirely. From a science perspective, this is terrifying. Rewriting matter on a planetary scale would require near total control of atomic bonds, perfect synchronization, energy inputs comparable to planet-binding energy. But unlike a laser blast, this kind of weapon wouldn't need to overcome gravity violently. It would essentially sidestep that problem, which makes it paradoxically more dangerous than the Death Star and even less controllable. And lastly, let's look at Galactus, the cosmic planet eater from the Fantastic Four. One of the most famous planet killers in science fiction isn't a machine at all. Galactus doesn't blow planets apart, it doesn't fire beams or crack crusts. He consumes planets, draining them of energy to survive. At first glance, this sounds just as absurd as the Death Star, but scientifically it's actually a little more coherent. Why? Because the Doomsday Machine in Star Trek like that, Galactus isn't trying to overcome gravity explosively. He's harvesting stored energy. Planets contain gravitational energy, thermal energy, chemical energy, nuclear energy. If a sufficiently advanced being could extract even a tiny fraction of that energy efficiently, the yield would be enormous. In principle, Galactus is performing a planetary scale energy harvesting. That already makes it more plausible than most superweapons, including the Death Star. However, Galactus immediately runs into the same enemy as the Death Star: thermodynamics. Extracting energy on this scale would generate vast amounts of waste heat. That heat has to go somewhere. A being consuming planets would need extreme heat dissipation mechanisms, exotic matter states to avoid self-destruction, or physics that somehow allow entropy to be exploited elsewhere. Otherwise, Galactus wouldn't starve, he'd overheat. In effect, Galactus is less like a god and more like a walking Dyson sphere with a metabolism problem. Whether it's the Death Star, Starkiller Base, or Galactus, the lesson is kind of the same. The more power a system tries to wield, the more violently physics pushes back. Planet killers don't fail because villains are stupid. They fail because the universe has limits, and no amount of cinematic menace can escape thermodynamics. So, could any planet killer version ever work? A full planet destroyer? Almost certainly not. But scaled down versions? Much more plausible. Realistic sci-fi alternatives would include things like planet-cracking asteroids, stellar-induced climate collapse, orbital kinetic weapons, or artificial gamma-ray bursts. These would all be devastating, they'd all be horrifying, and they'd all be far more achievable than a Death Star. So, final verdict. The Death Star is a masterpiece of science fiction. But in real physics terms, it fails on energy generation, energy storage, heat dissipation, structural integrity, beam coherence, and basic survivability. Ironically, the Death Star wouldn't destroy planets, it would destroy itself. So the next time you see a planet explode on screen, remember, the real universe is far more stubborn and far more dangerous than fiction gives it credit for. If you enjoyed this breakdown, subscribe for more episodes where I separate cinematic myth from real science. And let me know in the comments, which sci-fi superweapon should I analyse next?